After the previous video, we already know how to write functions. And we know that functions help us to take some code away from our main function and throw it into different functions, and then we can reuse those. But for now, we can only reuse them within the same binary file, or at least within the code that generates the same binary file. So what if we want to use them more than just in one file? For that, we need libraries. For those of you who have watched my videos for a while, you already know that these are the special symbols that I use on the slides. Feel free to pause the video if you need a refresher. So let's talk about libraries. Let's talk about what they are and how to use them. And in order to do that, I want to start with an example. Let's say I want to write this new amazing machine learning framework. And our particular machine learning framework is going to be pretty dumb because it has to fit on the slide. So in our case, our machine learning framework is basically just one function. This function is going to predict numbers, and the function looks something like this. If you need a refresher on what is a function, then feel free to go back to the previous video and watch that one first. But generally speaking, it takes a vector of numbers. If you don't know what a vector is, I have a video on that too. And it outputs another number. And we would like to use this function. For now, we use this function in the main. And I will not go over this function because it's not really that important, and I will leave it to you as a small homework to just read the function and understand what it does and why it does what it does. It's not that complicated. So let's go back to our main function, and in our main function we actually use this function. We call it to predict the numbers given the input 1 and 2, and we expect the output 3. Cool, so we have this function, but it's not particularly useful because for now we just use it within this main function, which is just testing that it actually works. But what if we actually want to use this? And at that, what if we want to use it at multiple places? And let's say, to give you a concrete example, let's say we want to write these two binaries, like two programs. One is to predict the prices on the houses, and the other one is to predict the price of the Bitcoin. Both of them can make use of the machine learning library that we've just written. So now the only question that there is to answer is, how can we use that function within these new binaries? And the obvious solution would be to just take that code over and copy it into these new binaries. So everybody who thinks this is a good idea, raise your hand. I'm not going to be able to see it, but you can still do it. I'm not sure this is a great idea. The reason for this is that now the code is duplicated, right? So we have the code in one place and in another place, and then our test is still there. So now we have 3 places where our code lives, and this is bad, right? So if you want to change the implementation of our machine learning framework, we now have to do it in all of the 3 places. And the main problem with this, the main problem at least for me with this, is that I have to remember that I have it in multiple places. I have to maintain it either in my head or in some notebook or wherever, I don't know where, that I have this code in multiple places. And I will definitely forget. And when I forget, there will be bugs. And I will spend my time on searching on these bugs, and it's not a nice place to be. So let's throw away the idea of just copying the code and try not to do that. There is a better solution to this. The better solution is to use header files. We've already touched upon the header files when we dissected the Hello World program at the start of the course. But today we're going to go much deeper into what are headers and how to use them. So the way we go about it is we take our function, or the whole framework, many functions, and we put them into the header files. In this particular case, let's put them into a header called ml.h. It's not a particularly good name because it's very short, but I need to fit all of this on the slide. So ideally I would call it machine learning.h, but well, at this point we'll just stick with the ml.h. So now we have this ml.h file, and this is again just a text file, so we can just take the code over and copy it there. I will skip the details of that function on the slide because again it has to just fit on the slide, and I would like to give an overview of everything on one slide and not split it over a couple. So we copied our code and we put it in the header file, and now we want to actually use it in our 2 other binaries. And the 2 other binaries would be the predicthousing.cpp and the predictbitcoin.cpp. The way we do that is we include this header file into those files. So we include our ml.h file into both. And see, now the code for our machine learning framework just lives in one place. It lives in the header file, and it's used in two places. So cool, right? We can reuse our code. Actually, we've just discovered what is a header-only library. So a library that has only headers, which basically just means that all the files that are in our library are all header files. And all of those header files we can include into whichever places we want them to be used in. And please remember that include is a preprocessor directive. We talked about this before, that basically just takes the contents of the header file and just verbatim copies them into wherever we call the hashtag include. And maybe a small hint here, when you have multiple headers, you start with your headers, like the ones that come from your project, then you go to the ones that come from external libraries, and then you go to the ones which are standard, like vector, string, and stuff like that. Okay, so we have our first header-only library, and there are pros and cons to this. The pros are that the compiler basically is able to see all the code, right? So if we have a bunch of headers and we include them into a bunch of binaries, the compiler is actually able to see all the code as if it was in the binaries in the first place. So it can optimize whatever it wants, and the compilers are really good at optimizing things. And the compilation actually remains very simple. We just need to provide the folder in which the includes live with the -i flag. But there is no free lunch, so there are also cons to this. And the main cons is that we always recompile our code. Whenever we have these includes in multiple binaries, let's say our project has hundreds of binaries, and now we include in all of these hundreds of binaries the same code from the same header files. Now all of these binaries will contain the same code, and we will have to compile them. And it can actually take a lot of time. So on the big projects, like if you go to a big company and you work on a big project, it's kind of common to see compilation times of like half an hour, a couple of hours. So if you now increase this compilation time by a factor of 2 or a factor of 10, if you just spread your code over a couple of files, it can actually accumulate pretty quickly, and you really don't want that. The next issue is that whenever you change something in any header that is included in some other binary, you will actually have to recompile everything. You will have to recompile all of the binaries that include this header because, well, the code changed, and so the code in those binaries has changed. Another issue is if you want to now ship your code to somebody, if you want to share the code with somebody, then they will actually see the actual code. They will see the logic that you've implemented. And returning to our machine learning framework is if our function were not that simple as it is, and it would actually have some secrets that we have in our heads, then we wouldn't really want anybody to see them. We don't want them to have access directly to the code that we wrote. Okay, you might have noticed that on a slide before we had the Pragma ones at the top of our header. Well, it starts with a hashtag, so you already probably know that it's a preprocessor directive. All of them start with a hashtag. And it ensures that the header is included exactly once. So if we include our header multiple times, it will only be included once. There are technically some compilers that don't support this, but I've never worked with one. I think most of the modern compilers actually do. In case you don't want to think about the compilers and you just want it to work, then your way is the include guards. The include guards are a little bit more error prone, but it's easily fixed with the tooling and having a proper editor setup. So what are the include guards? They are again a couple of preprocessor directives which basically define a certain macro and only contain the code below it if this macro is not defined yet. So let's look at the small example on the screen here. We check by calling the if and def, so like if not defined, folder file _h, that's the name of our macro, and if it's not defined, then we define it, and we follow along and look at all the code below it until the end if statement. But if it would be already defined, which means, let's say we include the file twice, and the second time this macro will be defined, this code will just be skipped. And that's exactly what we want. We will talk a lot more about this when we start talking about the build systems. The main takeaway from this particular slide and from this discussion is that you should always use either the Pragma ones or the include guards. Otherwise, there will be trouble and your code won't compile. Okay, so let's actually talk more about how do we now avoid this problem of long compilation times. The way to do it is we can write the binary libraries, or the libraries that are compiled into the binaries. The way we do it is we put the declarations of the functions into the header files, and we move the definitions of the functions into the CPP files. And then we can compile the corresponding source files, so the ones where we put our definitions, to object files. Then we pack those object files into libraries, and then we link those libraries to the executables that we actually want to write. So now if we have a couple of binaries like our predict housing prices and predict Bitcoin price, we can just link the same library to them, which guarantees that the library is actually built only once and just linked to multiple targets. And that also solves the problem of changing the code. If we do change the code of our library, we can just rebuild that one library, and then we can relink it to all the binaries that actually use it. And sometimes we don't even have to do that. Now, this is all nice theory. Let's look at an example again. So let's go back to our example with our machine learning framework, and let's now look at how our ml.h file, our header file, has changed. And what you see now is that now our function ends with a semicolon and there is no implementation. That means that this is a declaration of our function. We just say, well, hey compiler, there is this function, but it's somewhere, you will have to find it. The somewhere where it actually lives is in the CPP file. So the CPP file we now create, called ml.cpp, and here we actually put the implementation of our function. And the main part to note here is that we actually include the ml.h, because we want it to be, well, somehow connected to the declaration of the function that we have in the ml.h. And just as a refresher, the predict prices binary will look exactly the same as it looked before. It still includes the ml.h and knows nothing about the ml.cpp. And it still calls the same predict number function from before. So we have these three files, they're all in the same folder, and we want to try to build them. So we call our compiler, we say that we want the C++17, we want to build the predict prices.cpp, we want the output to be the predict prices binary, and we want to tell it that the header files that we want live in the same folder. So we pass the -i dot. If we try to compile it, the compiler will not be able to do it. It will throw an error at us. And I urge you to actually go and copy the code over and maybe, fill in the gaps that I left in the example code and try to actually compile this code on your own to also see this error and familiarize yourself with this error to know what it means. You will see an error which is very similar to the one that you see on the slide. I compiled it on a Mac OS, but if you do it on a different system like Linux or the Windows subsystem for Linux, then you will see a bit of a different error, but it will be very similar to this one. So go ahead and do it. And what you can notice here is that there is some new words that we didn't see before. The words are, there is this LD, and then there is something with the linker, right? So in my particular case, the Clang complains that the linker command failed, so it fails to link. To do that, we can compile first into object files, and for that we still use our compiler, but we pass this -c flag. The -c flag stands for just compile it. So what it will do, it will take the ml.cpp in the first line, and it will compile it and output the file which is called mlstatic.o, which is an object file. And we can do the same for the mldynamic.o, and well, basically the static one is used for a static library, the dynamic one is used for a dynamic library, and we'll talk about the differences between them in a sec. So I just wanted to have it all here so that you know how to create the two types of them. And the main difference with the dynamic one is that we provide this -f pick, which stands for the position independent code, and is just to instruct the compiler that it should put the code into the binary form in a certain way. Also here we assume that all of our headers lived in the includes folder that we provide also into our command. And at this, we have this a bunch of .o files, which are the object files. And now we can pack them into libraries. So there are two types of libraries. There are the static libraries and there are the dynamic libraries. To create a static library, you basically just, you just jumble all of your object files together. You just put them into one archive, and this archive is usually done with the AR command. You can always just go to your terminal and type man AR to see what this command is. But generally speaking, it just packs the object files together in a way that is readable by the operating system. It's a bit more complicated with the dynamic libraries. I will not go into details of what happens there because it's really not that important and a bit convoluted. And then finally, now that we have the libraries, we can link them into our code. So remember that linker complaining? Now we will make it shut up. Linking is actually pretty simple. You just tell the compiler where to look for a definition of a declaration that it sees in a header file. So the job of a linker is to look into the object files, find the definition of that library, and tell the compiler, well, there it is, just use it. The command that we use to link our executable to our libraries is the same for static and dynamic libraries. So here we actually compile the main CPP again, but if we wouldn't, we could also use the object file for it. But for now, we actually compile it. But then there is a bunch of new flags that we haven't seen before. And these flags are the -L capital and the -L small. So the -L capital basically tells the compiler or the linker where to look for the libraries. Basically, it gives a folder where all of our library files, the .a and .so files lie. And the small l letter, it basically tells us which library do we want to use. In this particular case, the -lml will look into the folder and will try to find the libraries that are called libml.a or libml.so. There is a couple of things that are important in this command. One of them is that the -l flags have to come after the CPP or .o files, so after the main CPP in this particular case. And even though the usage of the command is the same for static and dynamic libraries, the output is a bit different. Like one is the statically linked binary and the other is dynamically linked binary. The difference between the static and dynamic libraries can be described in one sentence like this. We basically, when we have a static library, it's copied into the executable to which we link it. So the actual bit code, the binary code, gets taken and copied into the resulting binary, while the dynamic libraries just copy the reference to where to look for it. And then at runtime, a certain definition is found wherever it is, wherever it's linked to. Generally, the binaries with static linkage, they contain all the binary code from all the binaries that they require. That usually results in bigger binaries, which can be an issue for you if you are running on a very, very small system and you just don't have enough place to place your binary. But the benefit of this is that because everything is contained within this binary, you can take this binary and copy it over wherever you want, and it will work in exactly the same way. Now, if you have a binary with dynamic linkage or with dynamic libraries linked to it, then it will only contain the references to other libraries. And that makes it smaller because the references are smaller than the actual binary code. But that means that the dependencies that are linked in this binary are actually looked up at runtime, which means that they can be looked up relative to the current path or in some library path, which usually on the systems is still maintained as LD library path. Which means that if we move our binary or if we call it from a different folder, we might not be able to find our libraries, which actually causes a bunch of frustration for newcomers to C++. You can also always visualize the libraries that are linked to your binary by calling the LDD on Linux or the otool -L on macOS. And I leave it to you to actually compile a couple of static and dynamic libraries and then run these tools on them to see the output. In this course, though, we will mostly use the static libraries. The next important thing to think about is, what if we mix them together? What if we mix the header-only libraries and the compiled libraries together? Does it even work? And what should we care about when we do that? And Well, the answer to this is yes, we can do it, but we have to be a bit cautious. And let's dive into a couple of examples here. I will have a very simple example just to showcase what happens here. And let's say we have this header file print.h, and this header file basically includes the IO stream, and it can print any string that you pass to it. Again, if you don't know what an IO stream is, I have a lecture about this too. Cool. So this is all it does. It's not that complicated. And then we have two compiled libraries, foo and bar, or libfoo and libbar. And we will compile them as static, just for the sake of example. Both of them have a header and a CPP file, and they basically just define the foo and the bar function respectively. The foo prints the foo, the bar prints the bar. And then we write the other program, another executable that we want to link to our libfoo and libbar that will use them, that will use the foo and bar functions from them. So it looks something like this. It includes the foo.h, the bar.h, and it calls foo and then it calls bar. That's it. And if we try to compile it now, we will see an error. I don't want to show this error on the screen here because I want you to actually do it. I want you to take the code from the previous slide, take the code from this slide, put it all into a couple of files, and just compile it with the commands here. It shouldn't take too long. All the code is there. It's all compilable. So just go and do that. So once you see that error, you will see that there is a duplicate symbol that the linker sees. It doesn't link, so it compiles, but it doesn't link. Now, why? Why doesn't it link? And the answer is the so-called ODR. And ODR stands for one definition rule. The ODR states that there must be exactly one definition of every symbol in the program. That means your functions and your variables. So we now have two libraries, the foo.a and the bar.a, with the source files that both include the print.h and therefore have a definition of the print function. Again, we only have the print function within the print.h, but because the print.h gets copied into the foo.cpp and the bar.cpp, we actually have the definition of that function within those. And now when we try to link both the foo.a and the bar.a to our new executable, we get a linker error because now we have two definitions of this function, and that is not allowed by the ODR. I hope it all makes sense. I hope this gives you an intuition of what ODR is. It's not really that complicated, right? And that's where the inline comes to the rescue. You might have noticed that we had this inline in one of the previous slides before, on when we first showed the header-only library. The reason for this is that ODR does allow to have multiple definitions of the inline functions and variables for that matter. So if we mark a function inline, ODR will say, okay, fine, I see a couple of definitions of this function, but it's inline, so I will allow it. The thing that is very important to remember here is that once you put the inline there, you are the one who guarantees that all of the definitions of this function will be exactly the same. This is what the compiler will assume from this point on. It will see a couple of the print functions, and it will see that they're all inline, and it will just pick one random, and it will not tell you which one it picks because it assumes that all of them are exactly the same, because you are the one guaranteeing this. Okay, now there is a couple of things that you have to remember about inline, that inline can only be used in function definition, and usually that also happens within the header file. And technically inline also hints to the compiler that you want that function to, within this one binary where it will be compiled, to not be referenced to this one place to which it actually contains its binary code, but you want the binary code of the function to be placed into places where you actually call it. But most of the compilers nowadays ignore it as they know better than you do. But that being said, so you might have noticed that I've been really stressing that you are the one guaranteeing something now. And that means that you have to be careful. Because let's illustrate this. Let's illustrate what can go wrong. Let's change our foo and bar a little bit. Let's not have the print.h header anymore, and let's just implement a print function within each of the foo and bar.cpp. One prints foo, the other one prints bar, and it takes no arguments whatsoever. And both of those functions are inline. It's very important here. They are in the CPP files and they are inline. It's not the best practice, but I want to illustrate a problem here. And our main function basically still remains the same. We first call the foo, then we call the bar, and we compile it in exactly the same way as before. We create the object files, we put them into the libraries, and we link those libraries to our main executable. Now, if we call our main executable, what will be the output? Really take a couple of seconds and try to think what will happen after listening to what I said on the previous slide. Did you get it? Well, the answer is, in my particular case, it was bar bar. So not foo bar, but it could also be foo foo. It's unspecified, and we are again in the undefined behavior land, which is where we like finding ourselves in C++, I guess. But first, let's talk about what actually happened here. We now have basically two functions with the same signature. The definitions of this function are different and are in different translation units, foo CPP and bar CPP. And whenever I say translation unit, what I actually mean is I just mean a CPP file. It's a fancy word that usually just means a CPP file. Now we link them together when we build our main executable, and the compiler sees the two definitions. But because they're both inline, it will say, well, okay, I mean, they are definitely the same because they're inline, and I told you that you should guarantee that they're the same. So it will just pick one and ignore the other. And that's how we get to just printing two bars. And now finally, we can talk about how can we try to avoid this? How can we try to protect ourselves from making this type of errors? Well, the first thing to do is probably don't use inline in CPP files, unless you really know what you're doing. Maybe sometimes there is a reason for this, but generally speaking, you should not. Whenever you define functions in headers, you should be using inline there, because you never know if your library is going to be used within other libraries that are compiled. Even if you write a header-only library, you don't really know how it will be used after the fact. And if you think you do, you probably don't. And by the way, the same holds for constants from C++ 17 and up. So now you can do an inline const_expr constant, and it basically behaves the same way as the function would here. But our main weapon is to use namespaces rigorously. So if you have your project set up, then the namespaces usually follow the folder structure of your project. That's the good style. Like that's the one that I've seen in a bunch of projects, and that's the one that I like to follow myself. And at the same time, I urge you to use the anonymous namespaces in CPP files. So if you are in the CPP file and you want a temporary function, something like the print function from before, use the unnamed namespaces there. So in a summary, we can use libraries to reuse and share our code. And we basically have three options. We have the header-only option, and then we have two compiled options, the static library and the dynamic library. Each of them has their benefits and the downsides, which we discussed at length in this video. In this course, I will mostly be using header-only in combination with static libraries. And at this, I think now you know most of the stuff that there is to libraries, and see you in the next one. Bye.